Welcome to lecture 38. In this lecture, I'm going to talk about our universe. Recall that in lecture 37, we derived the balance equation for the geometry of the universe. Using a notation where we introduced the symbol omega for the ratio between the energy density epsilon and this combination, which we call the critical energy density epsilon c, we found that there's a balance equation between omega and the parameter kappa that denotes the overall geometry of space. We found that if we used an equation of state that relates the pressure to the energy density epsilon by a constant W, then the solution for the matter part of the Friedmann equation was given in equation 38.2, where the energy density is proportional to the scale factor A with a power that is determined by the equation of state. We then used these two equations in lecture 37 to find an actual solution for the scale factor A of t if we assumed kappa to be exactly 0, which corresponds to a flat universe. In this lecture, we want to now explore what happens when we have non-vanishing values of kappa. Okay, first recall that the value of kappa corresponds to the overall geometry of space. It takes three different values. One of them is kappa is 0, which corresponds to flat space or Ricci curvature equal to 0. And that is the same as having 0 cosmological constant, lambda is 0. If kappa is 1, then we have an elliptic geometry. The space is that of a constant positive curvature, so R is bigger than 0 everywhere. And we have a cosmological constant that's bigger than 0. Finally, for the case kappa is -1, we have hyperbolic geometries, and these are spaces of constant negative curvature corresponding to negative cosmological constant. We considered the case of the flat universe with kappa is 0 in lecture 37, and we found that an implication of kappa is 0 was indeed that corresponded to this parameter omega to be exactly equal to 1. Now let's look what happens if we have kappa is smaller than 0. If you look back at equation 38.1, this clearly implies that omega has to be less than 1. If omega is less than 1, this means that the energy density is less than the critical energy density, and we call this an underdense universe. By contrast, if kappa is bigger than 0, this implies that the density parameter omega is bigger than 1. The energy density is bigger than the critical energy density, and we have an overdense universe. Depending on the value of omega, we have different geometries in the universe. So it would be good to know what value we have in our universe for omega. The value of omega, because omega is just the ratio of energy density over the critical energy density, is given by the sum over all matter contributions. So we have omega is a sum that contains the contribution from matter. By this we mean matter that is made out of ordinary particles. We have talked about dust in earlier lectures of this course. And the other two components would be radiation. This could be photons, for instance. And finally, contributions from the vacuum energy or cosmological constant. Each of these contributions is slightly different in nature in that it corresponds to a different equation of state parameter. So we consider them as different forms of matter, and different forms of matter are distinguished by the respective equation of state parameter. So for matter, we have W is 0. If we, for instance, say that it's essentially dust, which is pressureless. For the radiation, we have something that is close to an ideal gas law. So for the energy density 3 times the pressure, that would mean that W is 1/3. And finally, for the cosmological constant, for vacuum energy, we would have a case where W is equal to -1. Because these different forms of matter have different equation of state parameter, the energy density that we had back in equation 38.2 scale differently. So if you plug these values of W back in equation 38.2, you find that the matter part of the energy density, the one that has an equation of state W0, scales as energy density is proportional to the scale factor to the minus third power. For radiation, if you plug in 1/3 for W, you find that radiation energy density scales as the inverse fourth power. And if you plug in the cosmological constant, you find that the energy density of vacuum energy scales as a constant. In addition to the omega on the left-hand side of equation 38.1, we also have this term kappa, the term that's proportional to kappa. We can also sort of interpret that as an energy density. And if we do so, the term would scale as an energy density that is proportional to the scale factor to the minus second power. So the main point is that all of these different contributions scale differently with the scale factor. So if you want to have a solution for the scale factor that has all these components, the evolution for the scale factor will be complicated because there's no simple solution that takes into account all of these possible cases at once. Let's now see whether we can connect these different relations between geometry and energy density by constraining them with observational data for our universe. So the biggest thing that has come out of observational data in the last decades, I would say, is that observational data suggests strongly that the overall omega for our universe today is very close to 1. Since the omega always has to be the sum of all contributions, omega matter plus omega radiation plus omega lambda, this means that the universe that we are sort of seeing is almost flat, and we can dissect the individual contributions that give rise to this observation. The first thing is that we can constrain the matter part of the equation, and we find that omega matter today is about 0.3 with an uncertainty of about 30%. So that means that in the big scheme of things, this is the energy density or the density parameter of the universe. About a third of that comes from matter. The contribution from radiation is essentially negligible. It's almost zero. So there's almost no radiation contributing to the density parameter of the universe today. If we take these two inputs, omega matter and omega radiation, since it has to be 1, which is another observational input, the consequence has to be that omega lambda is about 0.7. So the lion's share of the overall energy budget in the universe is such that most of it must be vacuum energy. About a third is radiation, and about a third of it is matter, and there's almost no contribution from radiation. Let's look at these results a little bit in more detail. So first, let's concentrate on radiation. We said that we have almost no contribution from radiation to the energy budget of the universe. We can get a little bit more detail on this. The only thing we need to put in is to see, okay, where does most of the energy budget in radiation in the universe today come from? Well, that clearly comes from cosmic microwave background, because these are the photons that are permeating the whole universe, and they greatly dominate over, for instance, the energy density from photons coming from stars today. So this radiation from the cosmic microwave background is almost black body, and it has a temperature of about 2.7 Kelvin. It's fairly cold. We can calculate the energy density for this radiation. For a black body radiation spectrum, the energy density for radiation is given by this law here, pi squared temperature to the 4/190 times 2 because of the two polarizations of the photons. So that is one part that we need to calculate omega radiation. The other part is the critical energy density, which we need as well. And for that, we sort of plug in today's Hubble constant, for which we have observational data. We find that the critical energy density today is about 5 GeV per cubic meter. Essentially, just to give you a sort of idea what that means, is that the critical energy density today is about 5 protons per cubic meter. So it's the energy density, rest mass energy density of 5 protons in one volume of cubic meter. So clearly that is a very low volume, but everything that's larger than this would be overdense, and everything that's less than 5 protons per cubic meter is underdense. But of course, as I said, the observational data today suggests that the universe is at about that level, 5 GeV per cubic meter. Anyways, for the radiation, we want to take the ratio between the energy density in radiation and the critical energy density today. And if we do that math using unit conversion, we find that omega radiation today is about 2 times 10 to the minus 5. So it's not exactly 0, but it's very, very small. It's definitely much smaller than the 30% from matter and the 70% from the cosmological constant. Let's focus now on the matter part. So as I said before, observational data suggests that today omega matter is about 30%. Most of the matter that we know of is in stars, and we can calculate the contribution from stars and also sort of throw in gas clouds in the universe and things like that. If we do that, we come up with an omega for normal matter, I would say, which I call omega stars, which is about 5%, 0.046. So if we do the math, then we find that the difference between the observational data for omega matter and the actual matter that we know of, which is in stars, is about 25%. So what that means is that most of the contribution to the matter is actually not in stars. It's in some other form of matter, and we actually have no idea what that other form of matter is. It's not stars, it's not gas, we really don't really know what it is. Because we don't know what it is, it's a mystery, and we like dark mystery, so we call it dark matter, because we are in the dark in what constitutes that matter in our universe. But it's the lion's share of the matter. Finally, let's look at the elephant in the room. The energy budget suggests that the contribution from the cosmological constant omega lambda today is about 70%. Unfortunately, we cannot at all calculate lambda. We cannot really estimate it. We can do a naive estimate by sort of essentially cutting off our results for quantum P theories and taking whatever is left there as the vacuum energy contribution. If we do that, we come up with an estimate of omega lambda, which is about 10 to the 120, which is quite a bit off from 1, about 120 order of magnitude wrong. So because we really don't know what it is, we call omega lambda dark energy, mostly because it sounds mysterious. And this is an open problem in physics and cosmology. We really don't know how to calculate that. We would presumably be able to calculate omega lambda if we understood how to consistently formulate a quantum theory of gravity, but we can't. So that's what we're stuck with at the moment. Finally, let me mention a problem that comes out from these observational data of our universe. So as I said before, the observational data suggests that the omega radiation is about 10 to the minus 5, the omega matter is about 30%, and the omega from the cosmological constant is about 70%. We also know that these different forms of matter scale differently with the scale factor of the universe. The radiation scales as the -4th power of the scale factor, the matter as the -3rd power of the scale factor, and the dark energy scales as a constant in the scale factor. Now, Throughout the history of the universe, the scale factor changes dramatically. So it is not constant, it really sort of changes by orders of magnitude. So if A changes by order of magnitude, and these individual omegas change with different powers of omega, you would expect that if you took any random point in time, these omega should be very, very different, because you change something by orders of magnitude, you have different scalings in the different omegas, you would expect different sort of orders of magnitude for the individual components. However, what you see from observational data is that the matter part and the dark energy part are essentially the same. I mean, they only differ by a factor of 2, not by 20 orders of magnitude. So the question is, why is it that these two are so similar today? And even if you fold in radiation into the question, there's only a few orders of magnitude difference between the radiation and the other two parameters. So this is known as a coincidence problem, because the question is, why is it that today we have this coincidence that these two matter and dark energy contributions are about the same order of magnitude, when they could be very different and presumably have been very different in the past and will be very different in the future. So why is it that they are almost the same today? And with this, I will finish today's lecture.